Now we're going to take a look at the way to calculate the length of the portion of a polar curve. So a polar curve, the kind of polar curve we've been looking at, is a curve of the form r equal f of theta, where r and theta are the polar coordinates. And we can consider it as a parametric curve of the xy plane, because in the Cartesian coordinates xy, x is r times cosine and y is r times sine, and r along the curve is given by the function f of theta, so we obtain x and y as two functions of theta. In other words, we get parametric equations for the polar curve, where the parameter is the angle theta. But in the previous module, we've seen a formula to calculate the length of a parametric curve. Let me remind you what we've obtained. If you have a parametric curve of the parameter t that is traversed exactly once as t increases from a to b, and that is a smooth curve, which means that the functions x and y are both continuous, differentiable, and with continuous derivatives, then this formula gives the length of the curve for the values of the parameter from a to b. Namely, the length is given by the integral from a to b of the square root of the sum of the squares of the derivative of the two coordinates. So that means that in our case, we're going to have to calculate the derivative of x with respect to a parameter, which in this case is theta, and the derivative of y. So we have to calculate the derivative of both x and y, not with respect to t, but in our case the parameter is not t but theta. So we're going to use this formula to differentiate x and y with respect to theta. Specifically, because x and y are given by products, we use the product rule. So to differentiate x, we get derivative of f times cosine plus f times derivative of cosine, which is negative sine. Similarly, for y, we have again a product. We get derivative of f times sine plus f times derivative of sine, which is cosine. So when we take the sum of the squares of this derivative, for the first difference, when we square, we obtain the square of f prime times cosine, so that's f prime square cosine square, plus the square of f times sine, so we get f square sine square, and then minus the double product, 2 times f prime f sine cosine. When we square the derivative of y, we get f prime square sine square plus f square cosine square, and plus the double product 2 f prime f sine cosine. So the double products cancel out, and you see that in what remains we have f prime square times cosine square plus f prime square times sine square. You can factor out f prime square in these two, and cosine square plus sine square is 1, so we are left with just f prime square. And then we also have f square sine square plus f square cosine square. We can factor out f square, and then cosine square plus sine square is 1, so we end up with just f prime of theta squared plus f of theta squared. Another way to write that is r squared for f of theta squared plus r prime squared for f prime of theta squared. So we've obtained that the sum of the squares of the derivatives of the two coordinates can be expressed simply as r squared plus r prime squared. Plugging that in our formula for the length of a parametric curve, we obtain that the length, assuming that in our case we have a smooth curve that is traversed once as the parameter, which in our case is the angle, increases from a to b, then this length is going to be the integral from a to b of the square root of r squared plus the derivative of r with respect to theta squared, and we integrate with respect to theta. So let's take a look at an example. We want to find the length of the polar curve given by r equal 5 cosine theta for theta between 0 and 3 pi over 4. Now the first observation is that cosine is 1 to 1 between 0 and 3 pi over 4, and additionally we don't get two angles that are opposite to each other, that are pointing in opposite directions, so we don't have to worry about the same point being obtained twice for a positive and a negative value of r. All this to say, this curve is traversed exactly once as theta increases from 0 to 3 pi over 4, so the formula applies. And so the length is the integral from 0 to 3 pi over 4 of r squared, which is 25 cosine square of theta, plus the square of r prime. And r prime is negative 5 sine theta, so we obtain 25 sine square theta. Factoring 25, we get 25 times cosine square plus sine square, which is 1. So we end up with only square root of 25, which is 5. So we just have the integral from 0 to 3 pi over 4 of 5 with respect to theta. So that's 5 multiplied by theta evaluated between 3 pi over 4 and 0. In other words, 5 times 3 pi over 4, which is 15 pi over 4. Let's take a look at another example. Let's say we want to find the length of the polar curve r equals theta square for theta between 0 and 2 pi. R here stays positive, and theta square for theta positive is 1 to 1. So there is no repetition of any point, and the curve is traversed exactly once as theta increases from 0 to 2 pi. Therefore, we can apply our formula, and the length is given by the integral from 0 to 2 pi of the square root of the square of r and the square of r prime. Square of r here is theta to the fourth. R prime is 2 theta, so when I square it, I'm going to get 4 theta square. And in this theta to the fourth plus 4 theta squared, I can factor out theta squared, and I obtain the root of theta squared multiplied by theta squared plus 4. I can pull out the theta square out of the root, and because theta is positive, right, normally square root of a square, you get the absolute value of what was under the square, but in this case theta is positive, so what we obtain is simply the integral from 0 to 2 pi of theta multiplied by the root of theta squared plus 4. To integrate this, we observe that what we have outside the root is a constant multiple of the derivative of what we have inside. So we use substitution with u is theta squared plus 4, in which case du is 2 theta d theta. In other words, the theta d theta that we have inside the integral is just 1/2 of du, and what we have under the root is just root of u. So we end up with the integral, with 1/2 integral of root of u du. And for the bounds of integration, because we used substitution for a definite integral, we have to change the bounds. Specifically, when u is 0, when theta is 0, u is 4, and when theta is 2 pi, u is 4 pi squared plus 4. Now an antiderivative of root u, that's u to the 1/2, so an antiderivative is 2/3 u to the 3/2. And so we evaluate this antiderivative between 4 pi squared plus 4 and 4. 1/2 times 2/3 is just 1/3. Then we get this 4 pi squared plus 4 to the 3/2 minus 4 to the 3/2, which is 8. Let's take a look at one more example. We want to find the length of the polar curve r equal 1 plus cosine theta for theta between 0 and pi. Since cosine is 1 to 1 for the interval 0 pi, and r stays non-negative because cosine is between negative 1 and 1, that means that this curve is traversed exactly once as theta increases from 0 to pi. So we can apply our formula, and the length is given by the integral from 0 to pi of the square root of the sum of the squares of r and r prime. Plugging things in, when I square r, I get 1 plus the double product 2 cosine theta plus the square of cosine theta. R prime is negative sine. When I square it, I get sine square theta, which when I add cosine square gives me 1. and therefore we obtain the integral from 0 to pi of 1 plus 1, which is 2, plus 2 cosine theta. Factoring out the 2, we get the root of 2 times 1 plus cosine theta, and pulling the 2 out, we get the square root of 2 as a factor in front of our integral. And now we need to calculate this integral of square root of 1 plus cosine theta. We've discussed this kind of thing before. We would like to get rid of the radical, and to do that, one way to do this would be to use the double angle formula. Specifically, we can express the cosine of theta as 2 times the square of the cosine of half the angle, theta over 2, minus 1. Since inside the square root we're adding 1 to this, the 1 and negative 1 cancel out, and we end up with root 2 integral from 0 to pi of the root of 2 cosine square of theta over 2. I can pull out the 2 out of the square root. That gives me another square root of 2. So that gives me square root of 2 squared. And on the other end, when I have square root of cosine square of an angle, I should get absolute value of cosine of theta over 2. But since theta is between 0 and pi, theta over 2 is between 0 and pi over 2, and the cosine is positive. Therefore, I can just drop the absolute value, and I get square root of 2 squared, integral from 0 to pi of cosine of theta over 2. Square root of 2 squared is of course 2, and now an antiderivative of cosine of theta over 2 is sine of theta over 2 divided by 1/2, in other words multiplied by 2. So we obtain 2 times 2 multiplied by sine of theta over 2 evaluated between 0 and pi. So we get 4 multiplied by sine of pi over 2, which is 1, minus sine of 0, which is 0, so we obtain just 4. Now turn to the next video to look into how to obtain the area that is enclosed by sector, angular sector, and bounded on one side by a polar curve.